I want to talk a bit about the homework that I left you with for over the break. Many of you did just fine, but there were a few problems that came up, and so I thought that saying a few things here might be helpful. I'm not going to go over every proof in detail, but I will try to go over where I think the problem spots are. So let's start by looking at the first one. We're asked to show that AND distributes over OR. So that's what we have here. We have an AND statement abutting onto an OR. It's kind of like a multiplication over an addition. And over here we get the distributed version. First question is, how do we prove something like this? Well, it's an OR statement. Generally speaking, if you're trying to prove an OR statement, there's no reason to think that you can prove either disjunct by itself. There's no reason to think you can prove P and Q. There's no reason to think you can prove P and R by itself. The exception to that is that when you're already inside an indirect proof, and you've got an assumption that means if things are working properly that there's an implicit contradiction around the place, then you can sometimes adopt a different strategy. But we don't have that here. So what I would do is I'd start by extracting the information so that we don't forget about doing that, so it's available whenever we need it. One simplification gets us the P. We get Q or R by simplification once again from line 1. But now we need to actually start a subproof. We want to prove this disjunction. We don't have any obvious way of doing it except for going indirect. Actually, I take that back. There's a way that we could do it by using indirect proof, by using dilemma, and that would actually work out quite smoothly. But since most people try to do it another way, I think it's better to talk about what most people had on their minds. So, other than doing it by dilemma, which actually would work quite quickly, let's see what happens if we try to do it indirectly. The thing to keep in mind is that when you're doing an indirect proof, if what you want to prove is this whole disjunction, and you know that you can't prove the parts separately, then you have to assume the denial of the whole disjunction. Don't assume the denial of one of its parts, because you've got no reason to believe that you can prove one of its parts. So we make an assumption for contradiction. Sometimes when people are doing indirect proofs, they get a little bit worried or frightened, I think, and they think, well, maybe if I took a less complicated thing and assumed its denial, that would be easier. It's usually not true. So now that we've got this denied OR statement, the fact that we've also got De Morgan's means that things are actually pretty smooth from this point on. When we apply De Morgan's to line 4, we'll get not, P, and Q, and this is what makes it easy going, not, P, and R. That comes from 4 by De Morgan's. Now we can simplify. We get not, P, and Q. 5 simplification. We get not, P, and R. Same way. And then at this point, for some people, something funny happened. They noticed that they could do another De Morgan's, but for some reason, something went off the rails. So line 6 De Morgan's gives us not P or not Q. We had people who were getting not P and not Q, but remember, when you apply De Morgan's, the connective changes. The and is going to change to an or. So that's what we get when we do De Morgan's with 6. And likewise, when we apply De Morgan's to 7, we're going to get not P or not Q. Not R, rather. So, with that in mind, how is the proof going to work out? Well, the thing to do is make sure that you don't forget this stuff up here. You have P. With a double negation step, you do need it because of the way that the rule DS is written, you're going to end up with a contradiction quite quickly. 2 double negation gets us not P. So let's notice what's going on here. We've got not P. We can get not Q, and we can also get not R. Go ahead and do that. That comes from 8 and 10. by disjunctive syllogism, and we can get not R the same way. It's going to be 9 and 10 disjunctive syllogism this time. And now we're almost there. Go back up here again. We've got Q or R. Down here we've got not Q. That means we can get R. From 3 and 12, sorry, pardon me, 3 and 11, disjunctive syllogism, we get R. Now we have a contradiction. 12 and 13 contradict. So to complete the proof, let me just move this up a bit. All we need to do is put in our scope line. Pardon me, this was going to mess up the alignment a bit temporarily. That's okay, you get the idea. And once we've got our scope line in, we can conclude what we originally denied here. We can conclude the very thing we're originally trying to prove. It comes from 4, through 14 by indirect proof. Let's just realign this here. So the crucial thing was this. Once we extracted our information, we had to assume the denial of this whole OR statement. Applying De Morgan's gave us an AND statement that we could separate the pieces from. Then you also had to remember, when you're using De Morgan's here, use it correctly. Make sure that you get the right connective in here, that you swap the connectives. From there on, it was straightforward. Now, the next one, I've actually written out a part of the proof here. I'm not going to go through it in detail, except to notice this. We want to prove an AND statement. Usually the best way to prove an AND statement is to prove each of its parts separately. So what we did here is we assumed the denial of P or Q rather than the denial of this whole AND statement. Why? Because if it's really true, as it is, that you want to prove an AND statement in general by proving the parts separately, the thing to do here is to start by trying to prove P or Q. And so that's the explanation for the first assumption here. We assume not P or Q, an assumption for contradiction. A De Morgan got us a nice AND statement. When we simplified that, a step of disjunctive syllogism got us Q and R, and a simplification gave us a contradiction. So we proved the first conjunct. We proved P or Q. I didn't write out the rest of it because it would be much the same. You would assume not P or R to get yourself started proving the second conjunct. The proof would be very similar to this. It's just that where you had Q before, you'd have R. Once you completed that, you'd have P or R. You could put them together with conjunction. Straightforward. The next one was this, and this is actually probably the simplest proof of the lot. Let's just take a look and see what should go on here. You want to prove a conditional, so you will assume it's antecedent. You'll assume P and Q. But let's think what's going to happen when you do that. See if we can kind of peek around the corners. Once you assume P and Q, let's just write that out so we've at least got that in front of our eyes. P and Q, which is an assumption for P and R. What should happen? Well, when we simplify this, we can get P and we can also get Q. We can simplify this, however, and we're going to get, in addition, Q arrow R. That's the crucial thing. Once we have P, once we have Q, and more important, once we have Q arrow R, we can put the Q and the Q arrow R together in a modus ponens. That'll give us R. We'll already have P, we'll have R, conjunction will get us P and R. As near as I can tell, everybody did this one correctly, so I'm not going to say anything more about it. But it's just a reminder that when you've got a conditional, you have to do conditional proof. Carrying on, this one was a little bit more involved. It shows us that OR distributes over the arrow, whereas the previous one showed us that AND distributes over the arrow. Once again, you're trying to prove a conditional. So what you want to do is assume it's antecedent. Always be guided in your assumptions by what you're trying to prove. And if you are trying to prove a conditional, well, then just assume it's antecedent. That's the obvious and best thing to do. So this is an assumption for P or R. Now, this is a little awkward because we've got nothing here that we can easily extract information from. We're trying to get to P or R. Now, what can we do? Well, there's no reason to think we can prove P by itself. There's no reason to think we can prove R by itself. So what you do in a case like this is you simply go ahead and make an assumption for indirect proof. If nothing else is obvious, assume the denial of what you want to prove. I'm not saying that there's no other way that a proof like this could work out. I'm saying that go ahead and do the most straightforward thing. There's nothing wrong with it. So we've made an assumption for contradiction. Now we can do a De Morgan's. We get not P and not R. That OR turns into an AND, which will be very convenient because AND statements are easy to work with. So we've got an AND statement. Let's go ahead and simplify. OR simplification gets us not P and also gets us not R. Okay, we've got not P. We've got P or Q arrow R up here. So we can do a disjunctive syllogism step. We can get Q arrow R. That's from 5 and 1, or 1 and 5 if you like, disjunctive syllogism. And if you want, you can also go ahead and use that not P again to get Q, because that's obviously going to be useful. So from 2 and 4, by disjunctive syllogism once again, we get Q. And now we're almost home. We've got Q arrow R, we've got Q rather. We can get R by modus ponens. 7, 8, modus ponens. And now we have not R on one line, R on another line. We have a contradiction. So the contradiction is between lines 6 and 9. And we've completed our innermost subproof. So we can go ahead, put in the scope line. What do we conclude? Well, on line 3 we had the denial of P or R. So what we conclude on line 11, of course, is P or R. The justification is 3 through 10. Indirect proof. P or R was exactly what we needed to get. When we assumed P or Q, that was our goal, and so we've completed the first of the two subproofs, which means that we've got what we want. We got P or R from our assumption of P or Q, and that means that on our last line we have the very thing we had set out to prove. That from P or Q arrow, P or R. So that's 2 through 11. Conditional proof. Okay, so here, conditional proof because we're trying to prove a conditional. indirect proof because there was nothing obvious about another way to get P or R. I'm not saying that there isn't any way you could possibly have done it. I'm saying that there's nothing that obviously would have worked. So never be afraid to start indirect proofs, especially, as I said, now that we have rules for dealing with the denials of compounds. They're actually pretty efficient, and they work out a lot more quickly than you might have originally suspected. The only thing left was the theorem. The theorem that we were trying to prove was the highlighted bit right here. That was the theorem we were trying to prove. To prove a theorem, you don't have any premises. That means that to prove a theorem, you have to begin with an assumption. What assumption? We're trying to prove an OR. There is not the slightest reason to think that we could prove P arrow Q by itself. Not the slightest reason to think we could prove Q arrow R by itself. So we assume the denial of what we want to prove for contradiction. Now this one, let me move this further up the page here, will actually work out very nicely if we remember these various rules that we have for dealing with the denials of compounds. We can first apply De Morgan's here. We're going to get the denial of the first conditional and the denial of the second. So that comes from 1 by De Morgan's. Now what? Well, obviously we can simplify. So we'll go ahead and do that. 2 simplification, one more simplification gets us not Q arrow R. That's once again 2 simplification. And now that we have the rule for dealing with the denial of an arrow, this is going to work out really quickly. Now that rule comes in various forms, but if you notice quickly, you can see this, the easiest thing to do. From the denial of a conditional, you can conclude the denial of its consequent. From the denial of a conditional, you can also conclude its antecedent. So think about that. From 3, we can get not Q by the rule not arrow. This is one of these rules where we didn't force you into writing a conjunction. We allowed you to extract the parts that you need, just because that's what tends to be useful. So we've got not Q by, pardon me, forgot the line number here, 3 not arrow. 4 not arrow is going to get us Q. Okay, 4 not arrow gets us Q. Now, this not arrow rule is one that you really need to make sure you have well under control, because it's just an extremely useful rule, but it's not one that necessarily sticks quite as quickly in the memory. So now we have a contradiction. And that means that in spite of the fact that at first just looked like it might be a rather hairy proof, it works out quite quickly. We've got our contradiction, and we still have to have a scope line. By writing the scope line, we're saying that although we used the assumption as a tool to complete the proof, the conclusion doesn't depend on the assumption. The conclusion holds on its own. And the conclusion, of course, is the theorem that we originally wanted to prove. So there we have it. The justification is 1 through 7. So those are just some comments on the homework, but it's really important as we go forward now. We're going to be concentrating mainly on stuff about quantifiers, but in order to make sense of it, you have to have a really good grasp of the stuff about sentence logic that we've been doing. So if there are any questions about this or any problems about the examples that we give in the text, please make sure that you come see me.